Welcome to this explainer. Today we're diving into the fascinating, invisible journey of how the human-readable code we write actually transforms into pure hardware action. Because every time you open an app, play a game, or load a web page, there is an absolute masterclass in translation happening right under your fingertips. Let's unpack exactly how that works.
Here is the game plan for today. We'll start with the code translation problem, examine our two main contenders, compilation and interpretation, explore an awesome hybrid twist called JIT, and finally, we'll break down the real-world performance trade-offs. Okay, part 1, the code translation problem, bridging the language gap. To really get how software runs, we first have to acknowledge the massive language barrier between us and our machines. Just take a look at this. On the left, we've got human code. It makes sense, right? It's readable, like typing "print hello." But here's the thing. Your CPU, it definitely doesn't speak English, and it sure doesn't speak Python. It only understands what is on the right, raw binary machine instructions, literally just ones and zeros. Since our programming languages can't run directly on the hardware, a major translation step is absolutely mandatory before anything can actually execute. So let's look at part 2, compilation, the upfront approach. You can think of this method a lot like translating an entire massive book into a totally different language before you ever hand it over to a reader. In a compiled setup, you start with your source code, and then a heavy-duty program called a compiler takes over. It converts all of that code completely upfront into machine code, spitting out a ready-to-go executable program. Because it does all the heavy lifting before you even run the thing, what we call ahead-of-time compilation, the final program runs directly on the CPU. Languages like C, C++, and Rust use this, and the main perk? Pure, unadulterated speed.
But compilers don't just translate. They aggressively optimize your code beforehand. Take function inlining, for instance. Instead of forcing the CPU to jump to a completely different part of the program just to do some simple addition, the compiler literally swaps the function call with the actual math operation right there on the spot. It totally removes the overhead. It strips out dead code, it unrolls loops, and by doing all this upfront prep, the actual execution becomes ridiculously fast.
Moving on to part 3, interpretation, the live approach. If compilation is translating a book ahead of time, interpretation is basically having a live translator standing right next to you, frantically translating every sentence one by one as you speak. Instead of building a massive executable up front, you just hand your source code directly to an interpreter. While the program is running, the interpreter continuously reads the code, translates the instructions, and fires them off immediately, line by line. Languages like Python and Ruby traditionally rock this approach, and the huge win here is flexibility. You get super fast development cycles, debugging is way easier, and it's incredibly portable, since your source code can run on literally any machine that happens to have the interpreter installed. But man, there is a catch. Imagine you have a loop in your code that needs to run, say, 1 billion times. A compiled program just hands highly optimized instructions directly to the CPU to blast right through it. But in interpreted language, that poor interpreter has to read the statement, parse it, figure out what to do, and then execute it 1 billion separate times. It has to carry this massive burden of translating the exact same code over and over again on the fly. Which brings us to part 4. JIT, the hybrid solution, literally the best of both worlds. Because what if we could have the extreme speed of compilation and the dynamic flexibility of interpretation? Why choose between the pre-translated book and the live translator when modern engineering can actually just give us both? We want that quick startup, but we desperately crave the blistering speed. Enter the just-in-time, or JIT hybrid approach. This is the absolute magic behind modern JavaScript engines like B8 in your browser or the Java Virtual Machine. It kicks off by compiling your code into a quick intermediate format called bytecode. Then an interpreter starts running it right away, so it launches super fast. But here is the genius part. As it runs, the system stalks your code looking for hot paths, stuff that executes all the time, like our billion-time loop. Once it spots it, the JIT compiler swoops in on the fly, compiles that specific hot code into optimized machine code, and hot swaps it right in. Now, this introduces a really cool concept called the warm-up phase. When a JIT-powered app first launches, it's leaning heavily on the interpreter, so yeah, it might feel just a tiny bit slower at first. But it's learning. It's continuously gathering statistics about how you are using it. And because JIT learns your program's behavior during this warm-up, it adaptively optimizes those critical paths. Your application literally gets faster the longer you leave it running. It's an incredible mix of high portability and mind-blowing adaptive speed. All right, let's bring it all home with Part 5. Real-world performance trade-offs. Why this matters to you. How do these invisible, under-the-hood choices actually impact your phone's battery life or the apps you interact with every single day?
If we look at a head-to-head matchup, compiled languages win outright on raw runtime speed and startup time for sure. But they take a hit on portability since the code is locked to specific hardware. Interpreted languages, yeah, they're slower, but they totally dominate when it comes to flexibility, making cross-platform work a total breeze. And then there's the JIT hybrid right there in the middle, giving us adaptive speed and high portability, asking only for a tiny penalty in initial startup time while it warms up.
These trade-offs are exactly why different industries choose totally different tools. C and C++ are the absolute kings of game engines because look, when you're rendering a 3D world at 120 frames per second, you need maximum bare metal performance. Java is everywhere in big enterprise systems because it perfectly balances portability with heavy-duty power. JavaScript leans on those awesome JIT engines to keep highly interactive web apps feeling super snappy. And Python, it is basically the undisputed champ of AI because its dynamic nature makes developers incredibly productive.
But hold up, you might be thinking, wait, if Python is interpreted and interpretation is slower, why is it dominating AI and data science, which require massive computing power? Well, here's a fascinating paradox for you. Python only feels fast in AI because it's really just acting as an orchestration layer. It isn't actually doing the heavy math itself. When you fire up tools like TensorFlow or PyTorch, Python is just giving the commands. The real number crunching is happening underneath in highly optimized, ahead-of-time compiled C++ libraries. It gets the flexibility of interpretation on the surface and the raw muscle of compilation under the hood. Pretty brilliant, right?
At the end of the day, you might wonder why software engineers even obsess over these differences anymore, given how insanely fast modern computers are. But ultimately, performance really matters at scale. Imagine a massive cloud service. Saving just 1 millisecond per request, literally a thousandth of a second, might seem totally trivial to one person. But multiply that across billions of requests, that tiny efficiency translates to massive savings in server costs, way less latency, and dramatically better battery life on your phone.
So, the next time you open a lightning-fast app on your device, just take a second to consider the billions of tiny optimizations, the upfront compiling, and the real-time JIT translations happening right under the surface. As digital systems continue to process trillions of operations, how will this delicate balance between ultimate machine speed and dynamic human flexibility shape the very next generation of our software? Thanks for joining me on this explainer, and keep exploring the incredible systems that power